So this is a continuation from the previous lecture. In this particular lecture, we are going to talk about the flow around the cylinder or a two-dimensional circle, but with circulation. Now your problem basically is going to be the uniform flow past the circle, but with circulation. So now what we do is we add the stream function for the flow, stream function for the opposite doublet, if you would, and then we're going to add the stream function for the vortex. But the vortex is actually is responsible. The vortex is a result of the circulation. So now the circulation, assume the circulation is positive. So for positive circulation around this is what it's going to look like. It's the same, very similar to that previous problem. The only thing is now we have three components. We got the uniform flow, we got the doublet, and we have the circulation. So from our previous lectures, the uniform flow given at an arbitrary angle of attack alpha is given by this equation. And then the doublet is given by this equation, and we did this in the previous lecture. And this time we are adding the vortex, okay? So we're going to see how we're going to actually work with this. So this is the vortex with the circulation V, positive vortex, okay? So that's why there's a minus sign. So when alpha is equal to 0, my equation, actually my full equation, if I collect all the terms, is equal to this. And this constant is important because I want this particular term to be non-dimensional, okay? Because I want this term to be non-dimensional, I need to find that constant just such that it will make it such. Okay, so to do that, what we know is that when alpha is equal to, when psi has to be 0 on the surface, right? So it's 0 at 0 and pi, and r equal to a. We derived this last time. So if I just take some of these components and I put 0, let's say, sine of 0, this goes away. So then I'm left with this term only. So now from here, at r equal to a, you can see that your constant, this is for r equal to a, okay? So this is happening at theta equal to 0 and r equal to a. Okay, so I evaluate this, and this is the equation I get. And then when you put this plus there, right, this is nothing else than a division. And you can see that this term is equal to non-dimensional. So this will always make this term non-dimensional, which is what I'm really looking for. So now this is your stream function that we are working on. And the rest of the problem is very similar to what we did before. The only thing is that I have to carry this term around, which before I did not have any. So if I did the partial respect to r and 1 over r, then this is the component I get. So if I just did all this respect to r, and this is the expression I get, and then u of theta is equal to, I'm sorry, this is respect to theta, and then this is respect to r, and this is the expressions I get. So now, just note that when this is equal to 0, your circulation is equal to 0, your velocity has to be bigger than 0, okay? But the fluid, if the fluid is moving counterclockwise direction, okay, so this is happening in counterclockwise direction. But to ease our discussion here, we're going to introduce this new component with gamma dash, and gamma dash will be the opposite of the circulation that we had before. Okay, feel free to pause the video and take your notes. But I'm going to continue as the class goes on. I want to save some time since this is very similar to what we did last time. So don't want to go into so much details, if you would. At the surface of the cylinder r equal to a, you had know that this is 0, and then this term right here was the same term that we had before, but we are adding this extra term now, and this is because of the circulation, because your circulation was bigger than 0, was not equal to 0. Okay, and don't forget that I'm using this dash as the negative of gamma. Okay, so we substitute everything inside here. I get this big mega expression. That is my total velocity. If I want to find the stagnation point, you can see that this is 0 automatically. So I want to make this 0. So when I make this equal to 0 and r equal to a on the surface, remember this is on the surface. So then this is a squared, and this becomes a. This is 2 times pi, 2 times v infinite sine of theta plus gamma dash 2 pi a. And your sine of theta is equal to this expression. And then your stagnation angle will be the angle where distal sine of taking the sine inverse of this is your stagnation point. When this is less than 0, you can see that this is going to be less than 0 when my circulation is positive. We have it negative because right now it looks like this is a positive term, but in fact it's a negative term because this is minus gamma. Okay, don't forget that. Okay, so we have some interesting results that we can look at this. When we have this and what the stagnation points really look like. When gamma is equal to 0, right, then what happens is your stagnation points shift over here, right? That's where you find the stagnation points. But now when I have the circulation, because there's a circulation going on here, now my stagnation points have shifted. We actually have 4 different cases. The first case is 2 stagnation points, right, when there's no circulation at all. And then if your stagnation point is bound between 0 and 1, you're going to have 2 stagnation points. This is what this looks like. Okay, I got a point here, I got a point there. And then when this is actually equal to 1, where your stagnation, you're going to have exactly 1 stagnation point, and that's the stagnation point here. I call this curve C, because that will be this one curve that happens to be when you get there, this is what it looks like. Okay? Okay, so then you have, when this is bigger than this, this expression bigger than 1, then you really don't have any stagnation points. You can see that your curves actually go outside this curve, so there's no stagnation points on the cylinder. This stagnation point is not on the cylinder, it's outside the cylinder. These are going to have 2 stagnation points on the cylinder itself. Okay, so that's important. So now if you want to find the pressure, as we always did, right, where we do the v squared, and we know again this expression, I got this from here. I'm taking now v squaring this term, so I can replace that term in there. And then, you know, we do the same thing, p minus p infinite, divide this term, so everything can be non-dimensional, if you would. Then you get this mega expression. Remember, this was the expression that we got previously. This is the addition of the expression because now we have circulation. If the circulation was 0, then these terms will be completely 0. Okay? These are the responsible because of this circulation. Okay? Circulation bigger than 0. So if I'm going to plot this, it's a very interesting plot, right? So this plot right here, the black line is when I have no circulation at all. And then I want you to see what happens as my circulation starts increasing. What starts happening is the top of my cylinder, it basically becomes that number is right here that you see. You see, I go from small, and then it basically goes from here up and down. It basically, and it's going to end up somewhere here. That point right there that I see, that location right there, that's the top of my cylinder. But look what happens at the bottom of my cylinder. Bottom of my cylinder, my CP is actually decreasing, because remember, these numbers are going in negative. It keeps decreasing, decreasing at the bottom. So that actually produces some nice, interesting results here, so you can physically see what's really going on. Now, everything we are doing is, we are doing because we care, and we are looking for what the lift and the drag is on a surface. Remember that. That's the only reason we are doing most of this stuff, is to be able to predict the lift and the drag. So if I was going to be able to do that, then I can go here. This is what we call the Kura-Joukowski lift theorem. And basically what he's saying is your total force that to keep this cylinder in place is going to be equal to the enclosed surface area minus P n times ds, where n is nothing else given by this expression, and ds is given by this expression. Okay. So when I plug everything inside here, this is the expression I get, and for my P. So then this value right here that you see here, this value of P, this value is the pressure that we found in the previous slides. Let me find the slide for you. Remember when we said P is equal to P infinite and this term, and that's this V right here is given by this expression we found a couple slides back. Okay, then what I do is I plug that back inside there, and I plug this whole P inside this equation, and I get something big, and rearrange some terms, and you can write it like this. Okay, I can rearrange the whole thing as follows. Now, I'm sorry, I missed a slide here. There we go. So now this is the term that we have after rearranging a few terms. So now we're going to evaluate each one of the terms individually and see what happens. So if I take the first term right here, this term, and I take this term, I put them together, and you have to know that the integral of cosine over the period 0 to pi 0, same as sine. So this whole integral is 0. So these are constant numbers, right? Since these are constants, you can show that this whole term goes to 0. So now let's see what happens to the next term. Okay, so if I take this term and I multiply by these terms now, you can also show that this whole thing is actually equal to 0 as well. So now one term is left here. So we go with that term, and we see that the first term actually goes to 0. The second term actually gives me, this whole thing is equal to pi. So I can replace this whole thing in here, and this whole thing, and this gives me this expression. I can replace what this was, gamma b, that's equal to what's inside here. And then I can cancel out some terms. And at the end of the day, what you end up with is P is equal to, F is equal to this load right here. Now, note that this is the force required to keep the cylinder on hold. This is not the force actually, it's not the force acting on the body. Okay, so if I take this plus the force acting on the body, that has to be 0. So from here, you find that this is equal to this. And if I compare, you see that your D is equal to 0, and your lift is actually equal to its expression. So from here, this is the D'Alembert's paradox, which says that D is equal to 0. And then this is the Kura-Joukowski theorem that says L over B, the lift per unit span will be minus rho V infinite times gamma. Remember, gamma was minus F. So this is minus becomes plus. It becomes minus again because I want in terms of the true flow circulation. Okay, So basically what we have done is take a non-lifting flow over a cylinder, add the vortex, and we can see what happens to the lifting flow over a cylinder. And this problem will give me a value of lift, and it's going to give a value of drag, and drag will be 0, and this will be an expression given by this quantity right there, minus rho v infinite times gamma. Okay, so this is the conclusion of the flow around the cylinder with circulation. Now we're going to do 2 examples.